In this section, we're going to compare two population means using samples from each population. The way we'll compare the means is by finding the difference between the two of them, and then we'll try to see if one of them is more than the other, or if one of them is less than the other, or if they're just not equal to each other. So, because we're using standard errors and not standard deviations of the differences, the sampling model we will use is a student's T model. The confidence interval that we will build is a two-sample T interval. The hypothesis test that we will conduct is a two-sample t-test. In example 1, we have a population of adult men with a mean height of 71 and a standard deviation of 2.5. We have a population of women with a mean height of 65 and a standard deviation of 2.3. We're going to assume that both genders have heights that are normally distributed. So on the left, we're going to take repeated samples of size 30 from the population of male heights and calculate the sample means. If we did that, so if we took samples of size 30 over and over and over and over, we would have the sampling distribution of X bar for men. We know that when we take a sampling distribution for a mean, the average of all of our X bars will be the true average. So this sampling distribution will be centered at the true mu, which is 71. And that represents the average of all of the X bars for men. We know that when we take a sampling distribution, it is less spread out than the population distribution because the extreme values, so all the tall people or all the short people, if they're part of the sample, their heights will be averaged out with 29 other people in the sample. So it will be less spread out. So the standard deviation of all the X bars for men will equal 2.5 divided by radical 30. Okay, if we take repeated samples of size 25 from the population of women, we know that will be centered at the population mean of 65. This is the average of all of the X bars for females. This will be less spread out than the population distribution, so our standard deviation of all the X bars for females will equal 2.3 divided by radical 25. If we randomly take one sample mean for the males and one sample mean for the females and find the difference, and we do this over and over and over and over, so we take a sample mean for the males, sample mean for the females, find the difference, then we do it again, take a new sample of the males, a new sample of the females, and find the difference of those X bars. If we do this, we'll have the sampling distribution for X bar men minus X bar females. All right, we know that the difference, the average difference, will just be the difference of the averages. So if the men average 71 and the women average 65, then the average difference will be 6. So it says below, describe the sampling distribution of the difference in mean heights between men and women. So we know that the mean of all of the differences will equal 6. And then even though we're finding differences, if you find the standard deviation of a difference, you still add their variances together and then take the square root. It's like the Pythagorean theorem. So if we want the if we want the standard deviation for these differences, we would take the standard deviation for the men, square that, take the standard deviation for the women, and square that, and then we take the standard deviation make sure that's squared underneath. Take the standard deviation of that sum. So let's figure out what that is. All right, I got that this equals, so we'll go up here, this equals 0.648. So when you are describing a sampling distribution, remember you have to go through the SOCs or the CUS or the SCUMS, whichever acronym you want to use. So we'd have to talk about the center. It would be centered at 6. Unusual features probably doesn't have any because it's symmetric. The spread would be 0.648. We just found that. And the shape looks like it's unimodal and symmetric. What is the probability that the difference in mean heights of a random sample of 30 men and a random sample of 25 women is less than 5 inches? So when we calculate this probability, we do normal CDF. They say less than 5 inches, so 5 is our upper bound, which means our lower bound is -1 times 10 to the 99th. 5 is our upper bound. Our mean would be 6, and our standard deviation, I'm just going to write that whole thing. So it would be 2.5 over rad 30. This is squared plus 2.3 over rad 25. And this is also squared. And then the square root of that. Okay, I don't want to mess up, so I'm just going to write 0.648 under sigma. So this probability is 0.0614. For the conditions for this lesson, we're used to having 2 conditions. Now we're going to have 3, but these conditions have to be checked for both groups, so it's almost like we have to check 6 conditions. The first condition is the same as before, so it's the random / representative condition. And just make sure that you put this in context. Second condition is, and remember there are 2 ways to satisfy this condition. Either you can use the CLT, which means n is at least 30, or the population is approximately normal. Okay, and then the last condition is that the 2 groups are independent of each other. So when these conditions are met, we are allowed to find the confidence interval of the differences between the means of 2 independent groups. We're also allowed to conduct a hypothesis test when these conditions are met. Okay, the confidence interval formula looks like the one we've already learned for one sample. Instead of x bar, though, we have x bar 1 minus x bar 2. Plus or minus, and then we still have a t star there. And then the standard deviation for a difference is the sum of the variances, and then we take the square root of that sum. The degrees of freedom calculation is not as simple as it used to be. It used to be just n minus 1. When you're dealing with 2 samples, you have a really complex formula for calculating the degrees of freedom. So will you ever need to use that formula? Probably not. So when you run, or when you calculate the confidence interval on your calculator, they will give you the degrees of freedom. So that formula we will probably never use. Okay, in example 2, there's a study on sleep deprivation. No, it's a study on food intake after sleep deprivation for men who were randomly assigned to one of the 2 treatment groups, so either 4 hours of sleep or 8 hours of sleep. The amount of food intake was measured, and now we are supposed to compute and interpret a 95% confidence interval for the true difference in the mean food intake for the 2 sleeping conditions. So let's go ahead and put the 4-hour data in L1 and the 8-hour data in L2. So we're going to go to Stat Edit. Okay, this might be a good time to pause the video and then finish entering in all the data. Okay, so if we're going to calculate a confidence interval, you need to first check the conditions. So first condition is whether it's random or representative of the population. With experiments, usually you're not going to want a random sample selected. Instead, you're going to hope for random assignment, which we have. Okay, so condition 1 is men were randomly assigned to one of the two treatment groups. Condition 2 is either the CLT, which doesn't work because we have 15 subjects in each treatment group. So remember, each group has to satisfy the CLT, not the total. So we have 15 each, so that doesn't work. So we should then go ahead and check the normal probability plots for each group. Looks like they both look good. Trust me. So we're looking for roughly diagonal straight lines. And this indicates that the populations are approximately normally distributed. Okay, and now there's a third condition, and that is that the two groups are independent of each other. Looks like there's no mention of that, so we're going to have to assume that. We will assume the two groups are independent Right, we'll answer this question later. I'm going to continue the confidence interval process underneath. So we checked all the conditions. Since the conditions are met, we can use a student's T model with... Okay, so now you actually have to run the confidence interval on your calculator so that you can know the degrees of freedom. So the data should already be entered. Go to Stat, Tests, and scroll down to 2-sample t-interval. Alright, we had data. So my list 1, I'm going to use L1. List 2, I'm going to use L2. Frequency list we didn't use, so I'm going to put 1 for both. We are calculating a 95% confidence interval. So we put 0.95. Okay, and then it asks for pooled. Always say no for pooled, and I'll explain what that means in a future lesson. So then we go down one more line and we calculate the interval. And it gives us the interval, and then below that it gives us the degrees of freedom of 27.47. Always round this value up. You don't round this to the nearest. You round the degrees of freedom up. So we're going to say with 28 degrees of freedom. So since the conditions are met, we can use a student's t-model with 28 degrees of freedom to calculate a 2-sample t-interval. Okay, I'm going to be nice in this chapter and just let you guys write the interval. So it goes from negative 814.1 to 523.55. And we're also told to interpret the interval. We are 95% confident that the true difference in the mean food intake for the 2 sleeping conditions is between negative 814.1 and 523.55, and it's K cows. Okay, there's still one more question we haven't answered. Based upon this interval, is there a significant difference in the mean food intake for the 2 sleeping conditions? So because 0 is in the interval, that means there is not a significant difference. Because no difference means when you subtract them, you get 0. So because 0 is in our interval of plausible values, that means there is no significant difference, because theoretically they could be the same value. So I'll let you guys write that down. There is no significant difference in the mean food intake for the 2 sleeping conditions because 0 is contained in the interval.